Tonight, we're going to talk about something that gives every single particle in your body its mass, and for most of human history, we had no idea it existed. Not just undiscovered, completely unimagined. The question of why matter has mass wasn't even a question most people thought to ask. Mass seemed obvious. You pick something up, you feel its weight. You push something heavy, you feel resistance. Mass just seemed like a property that things had, the way color is a property, or temperature. It felt like something that needed no explanation, but it does. And the explanation, when physicists finally found it, required 40 years of searching, a machine the size of a city, and billions of dollars spent tunneling beneath 2 countries. The answer has a name: the Higgs Boson. And understanding what it really is changes how you see everything. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. Let's start somewhere familiar. Think about your own hand. Right now, the atoms in your hand have mass. The electrons orbiting their nuclei have mass. The quarks packed inside the protons and neutrons of every nucleus in every atom have mass. That mass is why your hand doesn't pass through the table when you set it down. It's why you have weight. It's why anything holds together at all. We take this so completely for granted that it almost sounds strange to question it. But here is what most people don't realize. Mass is not a built-in feature of the universe. It isn't automatic. It isn't guaranteed. There was a time, right at the beginning, when nothing had mass at all. In the first fraction of a second after the Big Bang, the universe was unimaginably hot. Every particle that existed was massless. Every single one of them moved at the speed of light. Think about that for a moment. The entire contents of the universe, all the matter that would eventually become every star, every galaxy, every planet, every person, all of it was flying around at the speed of light with no mass whatsoever. No atoms, no structure, no chemistry, just a blinding sea of massless particles racing through an infant universe. A universe like that cannot produce stars. It cannot produce planets. It cannot produce you. Without mass, particles cannot slow down enough to bind together. Without mass, gravity cannot pull matter into clumps. Without mass, nothing we recognize as physics, all reality, can form. Something happened. The universe expanded. It cooled. And somewhere around 1/1,000,000,000th of a second after the Big Bang, a field that fills all of space switched on. It has been on ever since. It is on right now, everywhere around you, passing through your body, through the walls of whatever room you're in, through the entire Earth. You have never detected it directly. Neither had anyone else for most of human history. But the moment it switched on, particles began to acquire mass. The universe changed from something that could not exist in any structured sense into something that could. Stars became possible. Planets became possible. Life became possible. That field is called the Higgs Field, and the Higgs Boson is what you get when you disturb it. The idea that such a field might exist was first proposed in 1964. A handful of physicists working independently realized that a new kind of field could solve a deep mathematical problem that was breaking their equations. They published their papers. The physics community took note, but there was a problem. There was no way to test whether this field actually existed. To probe a field like this directly, you would need to create a ripple in it. You would need to shake it hard enough to knock loose a particle, the Higgs boson. And the energies required to do that were far beyond anything any accelerator on Earth could produce in 1964, or in 1974, or in 1994. The technology simply didn't exist yet, so the idea sat. Physicists built it deeper into their theoretical framework. It became a central piece of the Standard Model, the master theory of all fundamental particles and forces. Every other particle the Standard Model predicted was eventually found. One by one, experimentalists tracked them down. The W boson, the Z boson, the top quark. Each discovery confirmed that the theory was right, but the Higgs boson remained missing. The last piece, the one that the whole structure depended on. Some physicists spent their entire careers working on the theory behind it without ever expecting to see it confirmed in their lifetimes. Then came the Large Hadron Collider, built at CERN, straddling the border between France and Switzerland. It is the largest and most complex machine humans have ever constructed. Its tunnel runs for 27 kilometers beneath the ground. It accelerates protons to within a fraction of a percent of the speed of light and smashes them together hundreds of millions of times per second. On July 4th, 2012, the two main experimental teams at the LHC announced that they had found it, a new particle, mass of about 125 billion electron volts, zero spin, number electric charge, matching the predicted properties of the Higgs boson to a precision that left almost no room for doubt. Peter Higgs, who had written the original paper 48 years earlier, was sitting in the auditorium. He was 83 years old. The discovery confirmed something profound. The reason matter has mass, the reason you exist, the reason anything physical exists, traces back to a single quantum field that turned on in the universe's first trillionth of a second and never turned off. We found the evidence for it. We built the mathematics to describe it and the machine to test it. But before we can understand what the Higgs boson is, we need to understand the problem it was invented to solve. Mass seems obvious until you try to explain where it comes from. Pick up a rock. It has weight. It resists when you try to throw it. Drop it and it falls. Everything about mass feels self-evident, almost boring. It's just a property that objects have. The way color is a property. The way temperature is a property. We measure it, we use it in equations, and we move on. For most of human history, that was enough. Newton built his entire framework of mechanics on mass. It appears in his second law as a given. Force equals mass times acceleration. You don't derive mass. You don't explain it. You measure it for each object and plug it in. Newton's physics is extraordinarily powerful. It sent spacecraft to the outer planets. It describes the orbit of every moon in the solar system. But it never once asks what mass actually is or why any object has it. Mass in Newtonian physics is simply a number you assign to a thing. The question of where that number comes from doesn't arise. It just is. For a long time, that was fine. Then physicists started peering inside atoms. They found protons and neutrons. Inside those, they found quarks. They found electrons orbiting nuclei. They found a zoo of short-lived particles that flickered in and out of existence inside accelerators. And as they tried to build precise mathematical descriptions of all these particles and the forces between them, something uncomfortable started to surface. The equations that worked best, the ones that predicted experimental results with extraordinary precision, had a problem, a deep one. They required certain particles to have no mass at all. Think about that for a moment. Not a small mass, not a mass that was hard to measure, exactly zero. The mathematics demanded it. And this wasn't a quirk of one obscure equation. The most successful theories physicists had built, the frameworks describing electromagnetism and the weak nuclear force, were built on a mathematical principle called gauge symmetry. This symmetry is not decorative, it is the reason the theories work. Strip it out, and the equations lose their predictive power entirely. Gauge symmetry is demanding. It imposes strict rules on what you are allowed to write down, and one of those rules, when applied to the particles that carry forces, is that those particles must be massless. A photon, the carrier of electromagnetism, is massless. That fits perfectly. Light travels at the speed of light precisely because it has no mass. The mathematics and the experiment agree completely. No problem there. But the weak nuclear force has its own force carriers. Two of them, in fact. Physicists call them the W boson and the Z boson. The weak force governs radioactive decay. It operates inside atomic nuclei, converting neutrons into protons, releasing energy in the process. It powers the nuclear reactions in the sun. Without it, stars don't shine. The W and Z bosons are the particles that carry this interaction between other particles, the same way photons carry electromagnetism between charged particles. Here's what experiments found. The W and Z bosons are not massless, not even close. The W boson is roughly 80 times heavier than a proton. The Z boson is about 91 times heavier. These are not small numbers. These are among the heaviest particles physicists had ever detected at the time. The W and Z bosons have enormous mass by the standards of fundamental particles, and no version of gauge symmetry allows that. This created a genuine crisis. The mathematics behind the weak force, when held to the same symmetry principles that made electromagnetism so precise, flatly insisted the force carriers should be massless. Experiments flatly insisted they were not. These two facts could not both be right, and yet they both were. What physicists tried first was the obvious thing. Just add the mass. Write it into the equations by hand. Assign the W and Z their observed values, and carry on. It sounds reasonable. It sounds like the kind of practical adjustment you might make to fit a theory to data. But it didn't work. It broke everything. Not in a subtle way. Not in a way that required careful analysis to notice. The moment you added mass terms by hand to a gauge theory, certain calculations produced answers that were not just wrong but infinite, probabilities that exceeded 100%, cross-sections that grew without bound. The numbers spiraled upward toward infinity with no mechanism to stop them. In physics, infinity is not a result. Infinity is a signal. It means the theory has lost contact with reality. A well-constructed physical theory should never predict infinite quantities for measurable outcomes. When it does, it tells you that something in the theoretical structure is fundamentally broken, that you have violated an assumption somewhere deep in the framework. Getting infinities from adding mass by hand was not just an inconvenience, it was the theory telling you that it had collapsed. And so physicists were stuck. They had two of the most successful theories ever written. Quantum electrodynamics described the interaction of light and charged particles so precisely that its predictions matched experiment to 10 decimal places. The framework describing the weak force was similarly powerful. Attempts to unify them into a single electroweak theory looked promising, but the weak force carriers had to be massive to match what experiments showed, and no mathematically consistent way to give them that mass existed. At least, none that preserved the symmetry the theories depended on. The W and Z bosons existed. Their masses were measured and real. But according to the best mathematics available, they shouldn't have been able to have those masses without destroying the theory that described them. Every particle physicist working in the early 1960s understood the problem. Most understood it was serious. Some suspected the answer would require something genuinely new. Not a patch or a correction, but a different kind of physics altogether. Simply tagging a mass onto a force-carrying particle caused certain mathematical predictions to spiral toward infinity, which in physics is another way of saying the theory has completely broken down. In 1964, 3 separate groups of physicists, working independently and largely unaware of each other's progress, all arrived at the same answer to the same problem. Think about what that means for a moment. 3 teams, 3 sets of calculations, 3 separate paths through the same dense mathematical forest. And all 3 groups emerged in essentially the same place within a matter of months. That kind of convergence doesn't happen by accident. When multiple researchers independently reach the same conclusion at the same time, it usually means the idea was waiting to be found. The physics was ready. The question had ripened to the point where the answer was almost inevitable for anyone willing to look hard enough. The first group to publish was Robert Brout and Francois Englert, working together in Brussels. Englert was Belgian. Brout was an American physicist who had moved to Belgium to work at the Université Libre de Bruxelles. Their paper appeared in August of 1964. They had been wrestling with the same core contradiction that was keeping theorists up at night. The equations describing the weak nuclear force required its carrier particles to be massless, but experiments showed those particles were anything but. Brout and Englert proposed a mechanism, a new kind of field, one that could interact with force-carrying particles and give them mass without destroying the mathematical structure of the theory. Their paper was precise, it was elegant, and it was largely ignored at first. Just weeks later, Peter Higgs submitted his own paper. He was working alone at the University of Edinburgh, thousands of miles from Brussels, with no knowledge of what Brout and Englert had just published. His first submission was actually rejected. The journal editor felt it lacked sufficient physical relevance. Higgs revised the paper and added a section. That addition was significant. He pointed out that the mechanism he was describing had a specific consequence. It predicted the existence of a new particle, a massive scalar boson that would be the signature of the field itself. That prediction, almost an afterthought in the original paper, would become one of the most sought-after objects in the history of science. The revised paper was accepted and published in October of 1964. A third group, Gerald Guralnick, Carl Hagen, and Tom Kibble, submitted their own paper in November of that same year. Kibble was at Imperial College London. Guralnick and Hagen were at that point working in the United States. Their paper was the most mathematically thorough of the 3. They developed the mechanism in greater depth and with greater rigor than either of the previous papers. All 3 groups had found the door. They just arrived at it from slightly different angles. Here's what most people don't realize about this. None of these physicists set out to discover the Higgs boson. The particle wasn't the goal. The goal was to save the theory. The mathematical framework describing the electroweak force was broken in a very specific way. The equations only held together if the carrier particles were massless, but they weren't massless. So the equations were wrong, or something was missing. These 6 physicists were trying to find what was missing. The particle came later, almost as a side effect, a consequence of the math rather than the target of a search. The core idea that all 3 groups proposed was the same in its essentials. There exists a field, not a force field in the everyday sense, not like gravity or electromagnetism, but a new kind of field with a peculiar property. Every other known field in physics, when undisturbed, settles to zero. Leave space empty, and those fields go quiet. But the new field that these physicists proposed would not do that. It would have a non-zero value even in perfect vacuum. Even in the most empty space imaginable, this field would be switched on, and particles passing through it, or rather interacting with it, would acquire mass as a result of that interaction. The stronger the interaction, the more mass. The weaker the interaction, the less mass. No interaction at all, and a particle would remain massless. This was not a modest proposal. Suggesting that all of space is permanently filled with a non-zero field that no one had ever detected, that was a radical idea. Physicists are generally cautious about adding new things to the universe. Every new field, every new particle, every new ingredient in the recipe has to justify its existence through evidence. These 6 theorists were proposing something with no direct experimental support at the time. They were proposing it purely because the mathematics demanded it. If the weak force was to make sense, something like this had to be real. The reaction from the physics community was mixed. Some theorists found the mechanism compelling immediately. Others were skeptical. The idea sat at the edge of the field for years, respected but unconfirmed, mathematically sound but physically unverified. The 1960s and 1970s would bring further theoretical work. Steven Weinberg and Abdus Salam would use the mechanism as a cornerstone in building the electroweak theory, which unified the electromagnetic force and the weak nuclear force into a single coherent framework. That work earned a Nobel Prize in 1979. The mechanism itself was becoming foundational to the Standard Model, but the particle that Higgs had mentioned in his revised paper, the scalar boson that would confirm the field's existence, had still never been seen. No accelerator in the world was powerful enough to create it. No detector sensitive enough to catch it. The mathematics said it had to be there. The experiments couldn't reach it yet. Brout died in 2011, 1 year before the discovery that would vindicate the work he and his colleagues had done in that remarkable single year. Englert and Higgs were awarded the Nobel Prize in Physics in 2013. The other contributors, Guralnick, Hagen, and Kibble, have remained less celebrated in the public eye, despite the importance of their work. 6 physicists, 3 papers, 1 year, 1 idea. Their solution was elegant, mathematically consistent, and almost impossible to test, which is why it would take nearly 50 more years to confirm. To understand the Higgs field, you first have to let go of the idea that particles are tiny solid balls bouncing around in empty space. That picture is intuitive. It's the one most of us carry around from school, but it's wrong, and the wrongness matters here, because the correct picture is the only way to understand what the Higgs field actually does. Modern physics describes the universe not as a collection of little objects moving through emptiness, but as a collection of fields. Fields everywhere. Fields filling all of space. Fields extending to the farthest reaches of the observable universe. Particles are not objects sitting inside these fields. Particles are the fields themselves, vibrating. A particle is a ripple. Think about that for a moment. Every electron, every quark, every photon of light, none of them are things. They are disturbances in something deeper. The most familiar example of this is light. When you turn on a lamp, photons travel from the bulb to your eyes. Those photons are not little pellets fired through empty space. They are ripples in the electromagnetic field. The electromagnetic field fills all of space. It has a value at every point in the universe. When that field is disturbed, when a charged particle accelerates, for example, the disturbance spreads outward as a wave. The gentlest possible ripple in that field is a single photon. Light is not something separate from the electromagnetic field. Light is what the electromagnetic field looks like when it vibrates, and this is true for every particle we know. There is an electron field. Electrons are its ripples. There is a quark field. Quarks are its ripples. Every type of particle corresponds to a field, and every field fills all of space. This framework is called quantum field theory. It is the most precisely tested scientific framework ever constructed. Its predictions match experimental measurements to 10 decimal places in some cases. When physicists say they understand something about the subatomic world, they mean they understand it through quantum field theory. So when the theorists in 1964 were trying to solve the mass problem, they were working in this language. The question wasn't simply why do particles weigh something? The question was why do the ripples in certain fields have a resonant frequency when the mathematics of those fields seem to demand they shouldn't? That is what mass means in this language. A particle has mass because its ripples have a natural frequency. A massless particle has ripples that can vibrate at any frequency at all. Now here is where the Higgs field enters. And here is what makes it unlike anything else in physics. Every other field in the standard model shares one property. In empty space, in a perfect vacuum, with nothing around, every other field settles to zero. The electromagnetic field in a vacuum has no value. The electron field in a vacuum has no value. Remove all the matter, remove all the energy, and these fields go quiet. Zero everywhere. That is what a vacuum means for these fields. It is the baseline, the resting state. But the Higgs field does not do this. The Higgs field, even in a perfect vacuum, even in the most empty region of space imaginable, does not settle to zero. It settles to a specific non-zero value. Everywhere, always. It is permanently switched on across the entire universe. There is no place you can go where the Higgs field is absent. Why does it do this? Because the mathematics of the Higgs field are structured differently from every other field. For every other field, the state of lowest energy is the state where the field equals zero. That is where they naturally settle. But for the Higgs field, the state of lowest energy is not zero. The math forces it to sit at a specific non-zero value. It's as if every other field is a ball sitting at the bottom of a bowl, and the bottom of the bowl is zero. The Higgs field is a ball sitting at the bottom of a bowl, where the bottom is not at the center. The lowest point is off to the side, away from zero. And the field sits there, permanently, everywhere in the universe, at that non-zero value. This is not a subtle distinction. It changes everything. Now, here is where the famous misconception comes in. You may have heard the Higgs field described this way. Imagine a crowd in a hallway. A celebrity walks through and gets slowed down by the people clustering around them. An ordinary person walks through and nobody notices them. The celebrity acquires more resistance, more effective mass, because the crowd interacts with them more strongly. This is the crowd analogy. It is everywhere. It is in popular science books, television documentaries, and countless articles. And it is wrong. Not slightly misleading. Wrong in a way that violates basic physics. If the Higgs field worked by creating drag, by resisting motion, it would slow particles down over time. The Earth would have long ago spiraled into the sun. Newton's first law says an object, T, in motion, stays in motion unless acted on by a force. Drag is a force. Drag changes velocity. Mass does not change velocity. Mass resists changes in velocity. These are completely different things. The crowd analogy confuses the two, and the confusion is deep enough that it will lead you to entirely wrong conclusions if you follow it. The correct picture involves vibration, not motion, not drag. Vibration. Think about a guitar string. When you pluck a guitar string, it doesn't vibrate at a random frequency. It vibrates at its resonant frequency. That frequency is fixed. It's determined by the string's tension and length. Every time you pluck the same string the same way, you get the same note. The resonant frequency is a property of the string itself, not of how hard you pluck it. A stationary particle is something like this. It is a standing wave, a vibration in a quantum field, oscillating at a fixed frequency, and that frequency is its mass. A massless particle has no preferred frequency. Its ripples can travel at any frequency, which means they travel at the speed of light. A massive particle has a resonant frequency it always returns to. It cannot travel at the speed of light, because its own field will not permit I.2. What the Higgs field does is give other fields a resonant frequency they would not otherwise have. When the Higgs field sits at its non-zero value everywhere in space, it interacts with the other fields around it. It stiffens them. It changes their structure in a way that creates a preferred vibrational mode. Before the Higgs field settled into its non-zero value, those fields had no resonant frequency. Their particles were massless. After the Higgs field settled, those fields gained a lowest natural frequency. Their particles became massive. The Higgs field did not drag the particles. It changed the fields those particles live in. It restructured the vibrational landscape of space itself. What does the Higgs boson have to do with any of this? The Higgs boson is simply a ripple in the Higgs field, just as a photon is a ripple in the electromagnetic field. When you disturb the Higgs field, when you dump enough energy into it through a high-energy collision, the field ripples. That ripple is the Higgs boson. It is the particle you get when you shake the field that is otherwise quietly sitting at its non-zero value throughout the universe. Detecting the Higgs boson was, in a sense, proof that the Higgs field exists and has the properties theorists predicted. You cannot directly measure the background value of the field, but you can measure its ripples. And that is what the Large Hadron Collider did in 2012. There is something worth stopping on here. The Higgs field is not made of anything. It is not a substance filling space like water fills a tank. It is a quantum field, the same category of thing as every other field in physics, except with this one extraordinary difference. It never turns off. It is not something you swim through. It is not something that pushes back. It is a feature of space itself, always present, always at its non-zero value, quietly determining the vibrational properties of every other field it interacts with. Every electron in your body has mass because the electron field has a resonant frequency. That frequency exists because the Higgs field shifted the electron field into a configuration where vibrating in place costs energy. The Higgs field is not a substance, and it does not create drag. It stiffens the fields that other particles live in, giving their ripples a resonant frequency, and that resonant frequency is what we call mass. Once you understand that mass comes from interacting with the Higgs field, the next question is obvious. Why don't all particles have the same mass? The Higgs field is everywhere. Every particle moves through it. Every particle is constantly immersed in it. So if the field is uniform, if it fills all of space equally, you might expect every particle to come out the other side with the same mass. But they don't, not even close. The electron has a tiny mass. The top quark has a mass roughly 350,000 times larger. That difference is not a small rounding error. That's a gap so extreme it demands an explanation. The explanation comes down to something physicists call coupling strength. When a particle interacts with the Higgs field, the intensity of that interaction determines how much mass the particle acquires. Think of it this way. Two guitar strings made of different materials will vibrate at different resonant frequencies, even under identical tension. The material itself determines how strongly it responds. Particles behave similarly. Each type of particle has its own characteristic coupling to the Higgs field. A stronger coupling means a stronger interaction. A stronger interaction means a heavier particle. The electron couples very weakly to the Higgs field. Its interaction is faint, almost reluctant. That's why it's so light. The top quark, on the other hand, couples with tremendous strength. Its interaction with the Higgs field is far more intense than any other known fundamental particle. That's why the top quark is the heaviest particle in the Standard Model, with a mass close to that of an entire gold atom. Same field, completely different response. Now consider the photon. Light has no mass at all. It travels at the speed of light because nothing with mass can do that. Why? Because the photon doesn't interact with the Higgs field at all. It passes straight through without coupling. No coupling means no mass. No mass means it travels at the maximum possible speed the universe allows. The Higgs field is everywhere, but the photon is simply immune to it, like a ghost walking through walls that everyone else has to push through. The W and Z bosons sit at the other extreme. They're the carriers of the weak nuclear force, and they're extremely heavy by the standards of fundamental particles. The W boson weighs about 80 times what a proton does. The Z boson is even heavier. Both of them couple strongly to the Higgs field. Their mass is enormous compared to the electron precisely because their coupling strength is orders of magnitude larger. This is why the weak force behaves the way it does. Heavy force carriers mean the force can only operate across tiny distances. The weak force is weak and short-ranged not because the underlying interaction is feeble, but because its messengers are so massive. So the Higgs field gives you the mechanism. But here's what's unsatisfying about that answer. It doesn't tell you why. Why does the electron couple so weakly? Why does the top quark couple so strongly? Why does the photon have zero coupling while the Z boson has such an enormous one? The Standard Model doesn't derive these numbers. It measures them experimentally and then writes them in. They're inputs, not outputs. You put them into the equations by hand because that's what the experiments told you, not because the theory predicted them from something deeper. Think about that for a moment. We have a theory that describes why particles have mass. It works. It's been confirmed, but it cannot tell you from first principles what the mass of any given particle will be. It can only say, here is the mechanism, now go measure the coupling for each particle and plug it in. That's a little like having a perfect recipe for baking a cake but having no idea why the ingredients combine the way they do. The recipe works every single time. You just can't explain the chemistry behind it. The range of masses in the Standard Model is genuinely staggering. From the neutrinos, which are so light their masses are barely above zero, all the way up to the top quark. The full span covers at least 12 orders of magnitude. That's a factor of 1 trillion or more between the lightest and heaviest known fermions, all of them interacting with the same Higgs field, all of them acquiring their mass through the same mechanism, but with coupling strengths that vary wildly and for no reason the Standard Model can currently explain. Physicists find this deeply uncomfortable. The Standard Model is extraordinarily precise in its predictions. Its calculations match experimental measurements to 10 or more decimal places in some cases. That level of accuracy is almost unheard of in science. But underneath that precision is a list of numbers that the theory simply accepts without explanation. The coupling strengths are on that list, 17 or so free parameters that you have to feed into the model from measurements. Why those particular values? No one knows. The theory offers no answer. This is sometimes called the flavor problem, or the mass hierarchy problem in a different sense than the hierarchy problem involving the Higgs mass itself. Why are there 3 generations of quarks and leptons? Why does each generation get progressively heavier? Why is the top quark so much heavier than the up quark, when both are the same type of particle, just from different generations? These patterns look like they might be pointing at something. Some deeper structure the Standard Model can't see yet, but so far no experiment has found it. The Higgs field explains where mass comes from. That is a genuine and profound achievement. Before 1964, there was no framework for answering that question at all. The Brout Englert Higgs mechanism gave physics a foundation it didn't have before. But standing on that foundation and looking out at the spectrum of particle masses, the obvious next question doesn't go away. It gets louder. Why these masses? Why these couplings? Why is the universe calibrated the way it is and not some other way entirely? The Standard Model gives you the mechanism but not the reason. And that gap is one of the things that keeps theoretical physicists awake at night. The universe didn't always have mass. That seems like a strange thing to say. Mass feels permanent. It feels like a basic property of reality, something that has always been there and always will be. But in the first moments after the Big Bang, the universe looked nothing like it does today. There were no atoms, no protons, no electrons with any mass to speak of. Every particle that existed was massless. And every massless particle travels at one speed, and one speed only, the speed of light. The entire universe was a kind of furious, brilliant chaos, particles racing in every direction at the maximum speed the laws of physics allow, unable to slow down, unable to bind together, unable to build anything at all. Think about what that means. No mass means no atoms. No atoms means no molecules. No molecules means no chemistry, no planets, no stars. The universe existed, but it was a universe that could not yet become anything. It was energy and motion without structure, brilliant and empty in the deepest possible sense. But something else was different in those first moments. Something even more fundamental than the absence of mass. The forces themselves were different. Today, we experience 4 distinct forces: gravity, electromagnetism, the strong nuclear force and the weak nuclear force. They feel completely separate. The force that holds electrons in orbit around a nucleus feels nothing like the force responsible for radioactive decay. But in the very early universe, two of those forces were the same force. Electromagnetism and the weak nuclear force were unified into a single interaction. Physicists call it the electroweak force. At the temperatures present in the first fractions of a second after the Big Bang, those two forces were indistinguishable. The mathematics describing them was perfectly symmetric. The carriers of the weak force, the W and Z bosons, behaved exactly like photons, all massless, all racing at the speed of light. The universe in those first moments had a kind of mathematical beauty that it no longer has. A symmetry so deep that forces we now think of as completely different were, in fact, one. That symmetry was not going to last. The universe was expanding, and as it expanded, it cooled. This is not a minor detail. The temperature of the early universe dropped with breathtaking speed. Within fractions of a second, the conditions that had sustained that perfect electroweak symmetry could no longer hold. And somewhere around 1 picosecond after the Big Bang, that's 10 to the negative 12 seconds, 1/trillionth of a second, something happened to the Higgs field. Before that moment, the Higgs field was at zero. It existed, but it had no value. It wasn't switched on. Particles moved through it the way you'd move through a room that contained nothing at all. There was no interaction. There was no resistance. There was no mass. Then the universe cooled past a critical threshold, and the Higgs field settled, not into zero, into a non-zero value. Everywhere, all at once, every point in the universe, simultaneously the Higgs field dropped into a lower energy state, one where its value was no longer zero but some constant, stable, non-zero number. Physicists call this a phase transition. It's the same kind of process that turns water into ice. Water above freezing has a certain symmetry. It looks the same in every direction. Ice doesn't. The molecules lock into a crystal structure. The symmetry breaks. What was uniform becomes ordered in a specific way. The Higgs field settling into its non-zero value was a phase transition for the entire universe, and it broke the electroweak symmetry completely. This is what physicists mean when they talk about electroweak symmetry breaking. The single unified electroweak force split. Electromagnetism went one way. The weak force went another. The photon remained massless, still moving at the speed of light, still carrying no mass at all. But the W and Z bosons, the carriers of the weak force, suddenly found themselves interacting with the Higgs field that now permeated all of space. That interaction gave them mass, enormous mass compared to the photon. And with that mass came a completely different behavior, a completely different force. What had been one force became two. What had been symmetric became asymmetric. What had been massless became massive. And it wasn't just the W and Z bosons. Every particle that couples to the Higgs field, every quark, every electron, every fundamental particle of matter acquired its mass in that same moment. The universe went from a place where nothing had mass to a place where the full spectrum of particle masses we measure today was suddenly locked in a trillionth of a second. Here's what most people don't realize when they hear about the Higgs field. This wasn't a gradual process. It wasn't something that happened slowly over the first few seconds or minutes of the universe's life. The electroweak phase transition happened fast. The universe cooled through a critical temperature, the field settled, and the structure of reality changed. Before that transition, no complex matter was possible. After it, everything was possible. Atoms could form, gravity could pull matter together, stars could ignite, planets could coalesce, life could eventually emerge. Without that transition, the universe would have remained what it was in those first moments, a sea of massless particles, racing in all directions, never slowing, never binding, never building anything. Photons of light can travel forever without interacting in ways that build structure. A massless electron cannot bind to a massless proton. Without mass, there is no hydrogen. Without hydrogen, there are no stars. Without stars, there is no carbon. Without carbon, there is nothing like us. The moment the Higgs field switched on is not a minor event in the history of the universe. It is the event that made the history of the universe possible. Every structure that has ever formed, every galaxy cluster, every nebula, every solar system, every ocean, every living cell, traces its origin back to that transition. The Big Bang created the universe, but the Higgs field made it matter. Everything we see, every galaxy, every star, every atom, every person exists because of something that happened in a trillionth of a second, 10 to the negative 12 seconds after the Big Bang, when a field that fills all of space quietly switched on. Proposing the Higgs field was one thing. Proving it existed was something else entirely. The theory was elegant. The mathematics worked. But physics doesn't run on elegant mathematics alone. It runs on evidence. And the evidence for the Higgs field required creating conditions that haven't existed anywhere in this part of the universe since the first trillionth of a second after the Big Bang. Here's the problem. The Higgs boson, the particle you produce when you disturb the Higgs field enough, doesn't just appear on its own. It can't be found sitting quietly in a sample somewhere, waiting to be isolated and measured. The energies required to shake the Higgs field hard enough to produce a real Higgs boson are extraordinary. We're talking about energies billions of times greater than anything generated by ordinary chemical reactions. Nothing in the natural world at human scales gets anywhere close to that threshold. Lightning doesn't do it. Nuclear reactors don't do it. The center of the sun doesn't generate particles with that kind of individual energy. To create a Higgs boson, you need a machine that can accelerate particles to nearly the speed of light and then smash them together head-on with enough energy to briefly recreate something resembling the early universe itself. That's what a particle collider does. It takes subatomic particles, usually protons, and accelerates them in opposite directions around a circular track, pushing them faster and faster until they're traveling at an almost inconceivable fraction of the speed of light. Then it steers the two beams into each other. The collision releases an enormous burst of energy in an incredibly small space. For a moment, conditions in that tiny region resemble the universe as it was in its first fractions of a second. Out of that energy, new particles can form. Heavy particles that haven't existed anywhere in the universe for nearly 14 billion years can flicker briefly into existence. The Higgs boson is one of them. Think about that for a moment. The only way to study a particle that gave the universe its mass is to build a machine capable of turning back the clock to before atoms, before protons, before anything with mass existed at all. But here's what most people don't realize. Even if you build that machine, you still won't see a Higgs boson directly. The particle doesn't last long enough. The Higgs boson is extraordinarily unstable. The moment it forms, it begins to decay. Not in microseconds, not in nanoseconds. In about 10 to the negative 22 seconds. That's 100 sextillionths of a second. The number is almost meaningless. It exists for less time than it takes light to cross a single proton. Before any detector can register its presence, it is already transformed into other particles. You can never catch it. You can only catch what it leaves behind. This creates a profound challenge. If you can't detect the Higgs directly, you have to infer its existence from the debris. When a Higgs boson decays, it produces specific combinations of other particles. 2 photons, 4 leptons, other recognizable signatures. So physicists design their detectors to look for those decay products. They measure the energies and trajectories of every particle coming out of a collision. Then they use those measurements to reconstruct what must have produced them. It's detective work at the most fundamental level. You arrive at the scene after the event is over, examine the evidence left behind, and work backward to determine what happened. There's another problem on top of that. The Higgs boson doesn't appear often. When 2 protons collide at the required energies, the vast majority of collisions produce nothing resembling a Higgs. The particle only shows up in roughly 1 out of every billion collisions. 1 in a billion. If you ran a billion collisions and got 1 Higgs, you'd be right on schedule. That means you need billions of collisions just to start accumulating any meaningful data. And each collision produces dozens of other particles, each one generating its own signal in the detector, each one creating background noise that has to be sorted through and understood before you can isolate anything interesting. So what are you actually looking for? Not the particle itself. What you're looking for is a statistical anomaly, a bump in a graph. When physicists plot the invariant mass of certain combinations of decay products across millions and millions of collisions, they get a distribution. Most of the time, that distribution is smooth. It reflects known processes that have nothing to do with the Higgs. But if a new particle is being produced and decaying into those same final states, it starts to show up as a slight excess at a specific energy. A small pileup of events at one particular mass value, rising above the smooth background like a hill you almost missed. That bump is the signal. That bump is the evidence. Not the particle, not a photograph, not a direct measurement. A statistical excess in a histogram, built up from hundreds of millions of collisions examined one by one. The challenge is separating that signal from everything else. The same decay products that a Higgs boson produces can also be produced by completely unrelated processes. 2 photons can come from sources that have nothing to do with the Higgs. 4 leptons can come from other interactions. The background is enormous. The signal is tiny. Physicists have to model the background with extraordinary precision, understand every known process that could produce similar results, and then ask whether what remains, after everything else is accounted for, is more than you'd expect from chance alone. The threshold they require is extremely strict, a 5 sigma result. That means the excess you're seeing has roughly a 1 in 3.5 million chance of being a statistical fluke. Physics doesn't call something a discovery until it clears that bar. For 40 years after the Higgs field was proposed, no machine existed that could even come close to generating the required energies. Physicists knew what they were looking for. They understood the theory. They had calculated what the particle should weigh, how it should decay, what signatures it would leave behind. The theory was complete. The prediction was clear. What was missing was the raw power to test it. What they needed was a machine unlike anything ever built, one capable of recreating, however briefly, conditions that last existed a trillionth of a second after the universe began. The Large Hadron Collider is not just the biggest machine humans have ever built. It is the physical answer to a question that had been sitting unanswered for nearly 50 years. Every tunnel, every magnet, every wire was placed there for one reason. Physicists needed to see the Higgs boson, and the only way to do that was to build something the world had never seen before. The tunnel itself runs for 27 kilometers in a circle beneath the border of France and Switzerland. That's roughly 17 miles of underground passage, wide enough to walk through, bored out of solid rock at a depth of around 100 meters. If you could somehow stand at one end and look toward the other, the far side would be beyond the horizon. It is not a laboratory in any familiar sense. It is closer to a city, buried underground, operating continuously, staffed around the clock by thousands of people. Inside that tunnel, two beams of protons travel in opposite directions. Each beam accelerates until the protons inside it are moving at 99.9999991% the speed of light. Think about what that means. The speed of light is roughly 186,000 miles per second. These protons are traveling just barely slower than that. Each beam completes 11,245 laps around the entire 27-kilometer ring every single second. They are circling faster than the human mind can track. And then the beams cross, and the protons collide. 600 million collisions every second. 600 million. The number almost stops meaning anything. To keep protons moving in a circle at those speeds, you need magnets of extraordinary power. The LHC uses over 9,000 superconducting magnets, some of them 15 meters long. To become superconducting, these magnets have to be cooled to an operating temperature of 1.9 degrees above absolute zero. That is colder than the average temperature of outer space, which sits at around 2.7 degrees above absolute zero. Outer space is warmer than the inside of the LHC. The entire magnetic system holds around 96 tons of liquid helium, and maintaining that temperature across a 27-kilometer ring is itself an engineering challenge that took years to solve. The LHC cost somewhere in the range of $10 billion to build. That number covers the tunnel, the magnets, the cooling systems, the computing infrastructure, and 2 decades of design and construction work. More than 10,000 scientists and engineers from over 100 countries contributed to the project. It was formally approved in 1994. The first beams circulated in 2008. From approval to operation was 14 years. From the original theoretical prediction of the Higgs boson to the first beams was 44 years. This was not a quick experiment. It was a multi-generational commitment to a single question. But here's what most people don't realize. Accelerating the protons is only part of the problem. The collisions themselves last far less than an instant. A Higgs boson, if produced, decays in about 10 to the negative 22 seconds. No detector on Earth can capture the Higgs directly. What the detectors capture instead are the secondary particles the Higgs transforms into as it decays. And those secondary particles arrive in every direction at once, mixed in with thousands of other particles from the same collision, from particles that had nothing to do with the Higgs at all. Separating the signal from the noise requires detectors of a scale and precision that had never existed before the LHC was built. The 2 main detectors are called ATLAS and CMS. ATLAS stands for Atoroidal LHC Apparatus. CMS stands for Compact Muon Solenoid, though there is nothing particularly compact about it. ATLAS is 46 meters long, 25 meters high, and weighs about 7,000 tons. CMS is 21 meters long and 15 meters high, but denser, weighing nearly 14,000 tons. Each one is roughly the size of a large cathedral. Each one sits underground at a collision point, surrounding the beam pipe from all sides, layered with different detector technologies designed to catch different types of particles. The innermost layers track charged particles. Further out, calorimeters measure energy. The outermost layers detect muons, which pass through almost everything else. The entire structure exists to reconstruct, from the debris of a collision, what actually happened in a space smaller than an atom. The number of sensors inside each detector is staggering. Atlas contains around 100 million individual sensor channels. CMS contains a comparable number. Each collision produces a spray of particles in dozens of directions, and each one of those particles has to be tracked, measured, and recorded. The computing system that handles this output is itself massive. The LHC generates roughly 15 petabytes of data per year. That's 15 million gigabytes, distributed across a global computing network spanning dozens of countries, processed by tens of thousands of computers running continuously. And yet, even with all of that, physicists were not looking for the Higgs directly. They were looking for a pattern, a slight excess, a bump in a graph appearing in the data at a particular energy value. The Higgs only shows up in roughly 1 in a billion collisions. Everything else is background, other processes producing similar-looking signals that have nothing to do with the Higgs at all. To see the signal above the noise required hundreds of millions of collisions, sophisticated statistical methods, and years of careful analysis. The detectors had to be calibrated precisely enough to measure particle energies to fractions of a percent. A systematic error of even 0.5%, compounded across billions of events, could bury the signal entirely or produce a false one. The scale of the engineering is one thing. What it represents is something else. Every bolt, every sensor, every line of code was put there because humans decided that knowing why matter has mass was worth this. Worth the cost, worth the decades, worth the careers of thousands of people who devoted their working lives to an experiment that might have found nothing. That commitment is inseparable from the machine itself. Two separate teams, Atlas and CMS, were analyzing the same data independently, each one a check on the other, because a discovery this significant could not afford to rest on the work of a single group. On the morning of July 4th, 2012, hundreds of physicists crammed into an auditorium at CERN that was designed to hold far fewer people. They lined the walls. They sat in the aisles. Some watched from overflow rooms on screens. Outside the building, hundreds more stood in corridors and gathered around monitors. The atmosphere was something between a scientific conference and a sporting event. People had flown in from across the world for this, not because the result was guaranteed, but because everyone in that building understood what was about to happen, or at least what might be about to happen, and nobody wanted to miss it. Peter Higgs was in the room. He was 83 years old. 48 years had passed since he sat down and wrote the paper that proposed what would eventually carry his name. 48 years of waiting. He had watched other experiments search and come up short. He had watched the Tevatron at Fermilab try and fail to reach sufficient energy. He had watched the LHC come online, watched it ramp up its collision energy year by year, watched the data accumulate. And now he was sitting in a chair in Geneva, waiting to find out if the universe had cooperated. Before we get to what was announced, it helps to understand what physicists actually mean when they call something a discovery. In everyday language, you discover something when you find it. In particle physics, it is more complicated than that. You cannot simply look at a detector and see a Higgs boson. You see collision debris. You see patterns in data. And patterns in data can look like signals when they are actually just random fluctuations. This is the deep problem with statistical measurement at this scale. Any individual bump in a graph could be noise, so physicists use a threshold. They require that any claimed signal be strong enough that there is only about a ONEIN 3.5 million chance it is a random fluctuation. That threshold is called 5 sigma, 5 standard deviations above the expected background. It sounds arbitrary until you consider the alternative, which is announcing the discovery of a fundamental particle and then being wrong. 5 sigma is not a cautious standard, it is an almost absurdly demanding one. Physics has been burned before by signals that looked real and then disappeared when more data came in. The 5 sigma rule exists specifically to prevent that. Both the ATLAS and CMS collaborations had been analyzing the same LHC collision data independently. Independently means genuinely independently. Separate teams, separate software, separate analysis pipelines, separate conclusions. The whole point was that they could not have both reached 5 sigma by making the same mistake. If 2 completely independent analyses of the same data both crossed the threshold, there was essentially nowhere left for doubt to hide. The presentations were given back to back, first ATLAS, then CMS. Each team walked through their analysis, their decay channels, their statistical results. The auditorium was almost completely silent for long stretches. When the CMS spokesperson displayed the final plot, the signal was unmistakable. A sharp excess in the data, sitting right around 125 gigaelectronvolts. A bump in a graph that represented, if the statistics held, the first direct evidence of the Higgs boson. CMS had crossed 5 sigma, and so had ATLAS. Independently, at the same mass, in the same decay channels. The room did not erupt immediately. There was a kind of stunned pause that happens when something you have anticipated for a very long time actually occurs. And then applause, long and sustained. Rolf Heuer, the Director General of CERN at the time, stood up and said simply that he thought they had it. Not "we have proven it." Not "the Higgs boson exists." He said he thought they had it, because even in that moment, even with 5 sigma from 2 independent experiments, the precision of physics language held. What they had found was a new particle, consistent with the Higgs boson, consistent with all its predicted properties. But confirmation required more work. What had actually been found? A particle with a mass of approximately 125 GeV, 0 spin, no electric charge, no color charge. Those properties matched the theoretical predictions precisely. The particle was decaying into pairs of photons, into 4 leptons, into the signatures that physicists had spent years predicting and years looking for. The signal was not ambiguous. It was not a hint. It was 5 sigma, replicated by 2 separate teams, appearing exactly where the standard model said it should appear. Think about what that means for a moment. A theory written down in 1964, built on abstract mathematics, describing a field that nobody had ever detected, predicted the existence of a particle at a specific mass with specific properties. And nearly half a century later, a machine that took decades to build and billions of dollars to fund, created that particle in a collision, and the particle decayed in exactly the way the mathematics said it would. And 2 separate teams of thousands of physicists confirmed the signal independently. The universe matched the equations. There were people in that auditorium who had spent their entire careers working toward this single result. Graduate students who had joined collaborations straight out of university, who had now been working on LHC detector systems for 20 years, who had never seen a result from any other experiment. There were senior physicists who remembered the theoretical papers from 1964 as new publications. The range of what that room held in terms of time invested and careers committed was extraordinary. Outside the auditorium, the announcement traveled fast. Physicists in laboratories around the world were watching the live stream. The press was there. The coverage was immediate and global. The phrase God particle appeared in headlines everywhere, a name that physicists had long disliked but could not prevent journalists from using. Inside the room, the man whose name the field carries sat quietly as the implications washed over a room full of people who had spent their professional lives chasing what he had first imagined on paper in Edinburgh in 1964. Peter Higgs, sitting in the audience 48 years after writing the paper that predicted this particle, was seen wiping tears from his eyes. The Higgs boson itself is strange, even by the standards of particle physics. And particle physics has very strange standards. You have particles that pass through entire planets without interacting. You have particles that exist in two states at once. You have force-carrying particles and matter particles, and particles that are their own antiparticles. The Higgs fits none of those familiar categories. It is something genuinely different, something that had never been seen before in nature. Start with spin. Every fundamental particle we know of has a spin value. Electrons have spin 1/2. Photons have spin 1. The W and Z bosons have spin 1. Gluons have spin 1. Quarks have spin 1/2. Spin is a quantum property. It has no direct equivalent in everyday experience, but every known fundamental particle carries a non-zero value of it, except the Higgs. The Higgs boson has 0 spin. That makes it the only fundamental scalar particle ever discovered. Think about that for a moment. Every other particle in the entire Standard Model has spin. The Higgs has none. It is unique in this respect among all known particles in nature, and that uniqueness is not a minor detail. It reflects something deep about what the Higgs actually is and where it comes from. The Higgs also carries no electric charge. It doesn't interact electromagnetically at all. It carries no color charge either, which means it doesn't interact through the strong nuclear force. Strip away those two interactions, and what you're left with is a particle that is, in some sense, remarkably inert. It interacts through the weak force and through gravity, like everything else, but it has none of the familiar charges that most particles carry. For a particle that is responsible for giving other particles their mass, it is surprisingly plain in its own properties. But here's what most people don't realize. You will never see a Higgs boson sitting still. You will never catch one in a detector. You will never point an instrument at it and record its position or measure its charge directly. The reason is simple and almost brutal. The Higgs boson is extraordinarily unstable. Once created, it decays almost immediately into other particles. Its lifetime is roughly 10 to the negative 22 seconds. That is not a small number. That is not even a number we have language for in everyday experience. 1 second contains 100 sextillion of those intervals. The Higgs exists, and then it is gone, before it has traveled even the width of a single proton. There is no slow decay here, no gradual disintegration. It transforms, instantly, into something else. So how do you find something you can never see? You look at what it leaves behind. When the Higgs decays, it produces other particles, and those particles fly outward into the detector. where they can be tracked and measured. The key is working backwards. If you know the energies and the momenta of all the decay products, you can calculate what they came from. Physicists call this invariant mass. The idea is that no matter how a particle decays, the total energy and momentum of the decay products, combined in the right mathematical way, always point back to the mass of the original particle. It doesn't matter that the Higgs was already gone. The math reconstructs it. This is the technique that made the 2012 discovery possible. Physicists weren't finding Higgs bosons. They were finding pairs of photons, groups of 4 leptons, and other combinations of particles, and then asking, what could have produced these? What parent particle, decaying right at the collision point, would leave behind exactly this signature? When you plot the invariant mass of those decay products across thousands and eventually millions of collisions, you expect a smooth curve. Background processes produce particles all the time, and their invariant masses spread across a range. But if a Higgs boson was being created and decaying, you'd see something extra, a bump, a slight excess sitting right at 125 GeV. That bump, small and precise, was the discovery. The 2 decay channels that proved most useful were Higgs to 2 photons and Higgs to 4 leptons. Both are rare. The Higgs doesn't decay to photons directly. Photons have no mass and the Higgs couples to mass. But it can decay through an intermediate loop of virtual particles and 2 photons emerge. This channel is useful because photons are clean signals. They're easy to detect, and their energies can be measured precisely. The 4-lepton channel is even rarer, but it produces an incredibly clean signature. 2 pairs of electrons, or muons, emerging from a single point. Almost nothing else in particle physics produces exactly that combination. When you see it, you pay attention. Neither channel is common. The Higgs itself only appears in about 1 in a billion proton collisions. And within those rare events, each decay channel captures only a fraction of the total Higgs decays. What this means in practice is that you need an enormous number of collisions running continuously over months and years just to accumulate enough events to see a statistically significant signal above background. The 5 sigma threshold that physicists demanded before declaring a discovery required not just one clean event, not even a handful. It required enough events that the probability of the signal being a statistical fluctuation fell to less than 1 in 3.5 million. What emerged from all of that was a particle with a mass of about 125 GeV, 0 spin, no electric charge, no color charge, matching the predicted properties of the Higgs boson with remarkable precision. It decays through the channels the theory predicted. Its coupling strengths to other particles match what the standard model calculated. It is, as far as every measurement since 2012 has been able to determine, exactly what Peter Higgs and his colleagues predicted in 1964. A particle that cannot be directly observed. A particle inferred entirely from the traces it leaves in its vanishing. It exists for about 100 sextillionths of a second, 10 to the negative 22 seconds, and in that vanishingly brief moment, it transforms into other particles, leaving behind only a trail of evidence that it was ever there at all. Here's something that surprises almost everyone when they first hear it. The Higgs field is not responsible for most of the mass in your body. That's not a caveat. That's not a minor footnote buried in the details. It's a fundamental fact about where mass actually comes from, and it changes the picture completely. The Higgs field is real. The Higgs boson was discovered. The mechanism works exactly as predicted, but what it explains is narrower than most people assume, and the gap between what it explains and what makes up the mass of everything you can touch is enormous. Let's start with what the Higgs field actually does. It gives mass to fundamental particles, the truly elementary ones: quarks, electrons, the W and Z bosons that carry the weak nuclear force. These particles interact with the Higgs field, and that interaction gives them a baseline mass. Without the Higgs field, they would be massless. They would travel at the speed of light. None of the chemistry that makes atoms, molecules, or living things would be possible. So the Higgs field is genuinely essential. It provides the foundation everything else is built on. But here's what most people don't realize. That foundation accounts for only a tiny fraction of the mass in the physical world around you. Take a proton. A proton is not a fundamental particle. It's made of quarks, specifically 2 up quarks and 1 down quark, bound together by the strong nuclear force. You might expect the proton's mass to simply be the sum of its quarks' masses. That's a reasonable assumption. It's also wrong. The quarks inside a proton have masses that come from the Higgs field, and those masses are genuinely small. An up quark has a mass of roughly 2 MeV. A down quark has a mass of roughly 5 MeV. Add those together and you get somewhere around 9 MeV for the 3 quarks inside a proton. But a proton has a measured mass of about 938 MeV. Think about that for a moment. The quarks themselves account for roughly 9 out of 938 MeV. That's less than 1%. The Higgs field explains less than 1% of the proton's mass. Where does the other 99% come from? It comes from energy. Specifically, it comes from the energy of the strong nuclear force, the force that holds the quarks together inside the proton. The quarks inside a proton are not sitting still. They're moving. They're exchanging particles called gluons at a ferocious rate. The gluons themselves carry energy. The quarks carry kinetic energy. All of this energy, the binding energy of the strong force, the constant motion of quarks, the constant exchange of gluons, contributes to the proton's total mass. And this is where Einstein's equation comes in. Energy and mass are equivalent. E equals mc squared. The energy trapped inside a proton by the strong nuclear force manifests as mass, not Higgs mass, strong force mass, binding energy mass. This is not a small distinction. Almost everything you have ever touched, picked up, or stood on is made of atoms. Atoms are made of electrons and nuclei. Nuclei are made of protons and neutrons. And the mass of protons and neutrons is almost entirely strong nuclear force energy, not Higgs field interaction. Your body has a mass of perhaps 70 or 80 kilograms. Of that, well under 1 kilogram comes from the Higgs mechanism. The rest is binding energy from the strong force, expressed as mass through E equals mc squared. A rock sitting on the ground, same story. A planet, same story. The mass of the observable universe is almost entirely strong force energy that has taken the form of mass. The Higgs field is responsible for a small fraction of it. So why does the Higgs matter so much if it only explains such a small percentage of everyday mass? Because without the foundation, the structure collapses. The quarks need some mass to behave the way they do. If quarks were completely massless, protons and neutrons would not exist in their current form. The chemistry of atoms depends on electrons having the mass they do. The weak nuclear force works the way it does because the W and Z bosons are massive. If any of these baseline masses were zero, the physics of atoms, nuclear reactions, and chemistry would be unrecognizable. The Higgs field doesn't give you most of the mass, but it gives you the conditions under which the strong force can do its work. Remove the foundation and everything above it comes down too. This reveals something essential about the layered organization of nature at different scales. The Higgs field works at the fundamental level, giving elementary particles their baseline masses. The strong force operates at an entirely different scale, binding quarks together and releasing enormous energy in the process. Understanding this crucial distinction helps explain why the Higgs discovery mattered so much, while recognizing that it accounts for only a small fraction of the mass in everyday objects. But it's worth sitting with how strange this actually is. The mass you feel when you pick something up, the resistance you feel when you push something heavy, almost none of that is Higgs field interaction. Almost all of it is frozen energy from a force operating at scales far smaller than atoms. A proton is roughly 1 femtometer across, which is 1 quadrillionth of a meter. The quarks inside it are confined in that space, whipping around, exchanging gluons, generating an enormous amount of energy in an extraordinarily small volume. That energy is what you're lifting when you pick up a stone. Einstein described the relationship between energy and mass more than a century ago, and for the ordinary physical world around us, his equation is far more directly relevant than the Higgs mechanism. This doesn't diminish what was discovered in 2012. Finding the Higgs boson confirmed that the mechanism giving fundamental particles their baseline masses is real and works exactly as predicted. That's a profound result. But physics is layered. The Higgs field operates at one level of the structure. The strong nuclear force operates at another level, and it dominates the mass budget of the visible universe by an overwhelming margin. What physicists found at CERN was the keystone of the foundation. The Higgs field built the foundation, but the structure sitting on top of it turned out to be far heavier than the foundation itself. The standard model of particle physics is the most precisely tested theory in the history of science. Not the most tested theory in physics, in all of science. Every field, every discipline, every framework humans have ever built to describe how reality works, none of them have been verified to the precision that the standard model has. Some of its predictions have been confirmed to 10 decimal places. Think about that for a moment. 10 decimal places. That's like predicting the distance from New York to Los Angeles and being accurate to within the width of a human hair. So what is it exactly? The standard model is a mathematical framework that describes all known fundamental particles and 3 of the 4 fundamental forces. It tells you what matter is made of. It tells you how those pieces interact. It accounts for electromagnetism, the weak nuclear force, and the strong nuclear force. It does not include gravity. We'll come back to that. But everything else, every interaction, every decay, every collision that physicists have measured in laboratories over the past 50 years, the standard model describes it with almost frightening accuracy. The particle content of the standard model is specific. There are 6 quarks: up, down, charm, strange, top, and bottom. Quarks are the constituents of protons and neutrons. They bind together in combinations of 2 or 3, held by the strong nuclear force, and they never appear alone. Then there are 6 leptons. The electron and its 2 heavier cousins, the muon and the tau, and 3 corresponding neutrinos, 1 for each. Neutrinos barely interact with anything. Billions of them pass through your body every second without leaving a trace. Then there are the force-carrying particles. The photon carries electromagnetism. The W and Z bosons carry the weak nuclear force. The gluons carry the strong nuclear force. That's 4 types of force carriers. And then, separate from all of them, sitting in its own category as the only fundamental scalar particle ever discovered, there is the Higgs boson. Every single one of those particles had been experimentally confirmed before July 4th, 2012. Every one except the Higgs. The top quark was found in 1995. The tau neutrino was detected in the year 2000. Gluons had been confirmed back in 1979. Particle by particle, the standard model had been assembled over decades, each new detection confirming another piece of the picture. But the Higgs remained absent. Predicted in 1964, searched for relentlessly, never seen. Here's what most people don't realize. The standard model didn't just predict that the Higgs boson should exist. The standard model required it. Without the Higgs mechanism, the mathematical structure of the entire theory falls apart. The W and Z bosons have mass. Experiments proved that beyond any doubt decades ago. But the symmetry principles built into the standard model's equations said those particles couldn't have mass. The only way to resolve that contradiction was the Higgs field. Remove the Higgs and the whole framework collapses into mathematical inconsistency. The Higgs wasn't optional, it was load-bearing. This is why the search lasted nearly 50 years. Physicists weren't hunting a curiosity, they were hunting the keystone. And when ATLAS and CMS both reported a 5 sigma signal at 125 giga-electron volts in 2012, what they were really announcing was that the keystone had been found. The standard model was structurally complete, a theory that had been built piece by piece across half a century by hundreds of physicists across dozens of countries, finally had all its pieces. The precision of the theory at that point is worth sitting with. The magnetic moment of the electron, a measure of how it responds to a magnetic field, has been calculated from the standard model and measured experimentally. The two numbers agree to 11 significant figures. That is not a coincidence. That is a theory that is genuinely, deeply, extraordinarily correct about how nature works at the subatomic level. No other framework in human intellectual history has achieved anything close to that level of agreement between prediction and experiment. But here's where satisfaction gives way to something more complicated. The standard model, for all its precision, is incomplete in ways that physicists cannot ignore. It does not describe gravity. Gravity is governed by general relativity, which operates on entirely different mathematical principles. And despite decades of effort, no one has successfully merged the two frameworks into a single consistent theory. That alone tells you the standard model is not the final word. It gets more unsettling. The standard model accounts for about 5% of the total energy content of the universe. 5%. The rest is dark matter and dark energy, two things that are inferred from their gravitational effects, but not described by the standard model at all. Dark matter has mass, which means it must interact with the Higgs field in some way, but how strongly and through what mechanism remains unknown. Dark energy is even more mysterious. The standard model offers no explanation for either. Then there is the matter-antimatter asymmetry. When the universe began, matter and antimatter should have been created in equal amounts. They should have annihilated each other completely, leaving nothing behind. But they didn't. Something tipped the balance. The standard model predicts a small asymmetry through a process called CP violation. But the asymmetry it predicts is far too small to explain the universe we actually observe. Something produced the excess of matter that became galaxies, stars, planets, and people. And the Standard Model doesn't tell us what. And the Higgs mass itself sits at 125 gigaelectronvolts. That number is what experiments found, but the Standard Model offers no deep reason for it. It's a measured value, not a derived one. When physicists calculate quantum corrections to the Higgs mass, those corrections want to push it toward far larger values approaching the Planck scale, which is 17 orders of magnitude higher than what was observed. Something is keeping the Higgs mass small. The Standard Model doesn't say what. This is the hierarchy problem, and it remains unsolved. The Standard Model was complete, and the moment it was complete, physicists immediately started listing everything it couldn't explain. Finding the Higgs boson answered the question physicists had been asking since 1964 and almost immediately replaced it with a dozen harder questions. Start with the most basic one. The Higgs boson has a measured mass of about 125 GeV. That's a specific number, a precise value that took decades and billions of dollars to nail down. Yet this crucial detail eludes most people. The Standard Model does not predict that number. It cannot tell you why the Higgs mass is 125 GeV rather than 200 GeV or 50 GeV or anything else. The mass is simply measured and inserted into the theory as an input. There's no deeper equation that spits it out. For a theory this precise, a theory that predicts other quantities to 10 decimal places, that feels deeply unsatisfying. The Higgs mass is a fact the Standard Model accepts but cannot explain. Think about what the discovery of the Higgs boson actually represents. Not just as a physics result, not just as a confirmation of a 50-year-old theory, but as a statement about what human beings can actually do when they commit, completely, to a single question. In 1964, a physicist named Peter Higgs sat down and wrote 4 pages. 4 pages describing a field that nobody had ever detected, that no instrument had ever measured, that had left no direct trace in any experiment ever conducted. He was describing something that had been present everywhere in the universe since the first trillionth of a second of its existence, and nobody knew it was there. That paper was 4 pages long. The machine eventually built to confirm it was 27 kilometers around. Think about that gap. 4 pages to 27 kilometers. 48 years of work connecting them. Thousands of physicists. Billions of dollars. A tunnel carved beneath the French and Swiss countryside, cooled to temperatures colder than outer space. Running proton beams at 99.999991% of the speed of light. All of it tracing back to 4 pages written by a physicist in Edinburgh who was trying to explain why the weak force behaved the way it did. The scale of that commitment is hard to fully absorb. And here's what makes it more remarkable. When Higgs wrote that paper, there was no guarantee the field was real. It was a theoretical proposal, a mathematical solution to a mathematical problem. The equations demanded something like it, but equations don't always reflect nature. Physics is full of beautiful theories that turned out to be wrong. The Higgs mechanism was elegant. It was consistent. But for 48 years, it was unconfirmed. Physicists worked with it, built on it, incorporated it into the Standard Model, taught it in graduate courses for decades, all while the central piece of evidence was still missing. That takes a particular kind of intellectual confidence, or perhaps faith is a better word. But here's what most people don't realize when they hear the story of the Higgs discovery. It wasn't just that physicists found a particle. What they confirmed is something much stranger. They confirmed that space itself is not empty. Every point in the universe, every cubic centimeter of what we casually call empty space, is threaded through with a field that has a non-zero value, not zero, not dormant, on, always on. The Higgs field doesn't turn off in the spaces between galaxies. It doesn't weaken in the void between stars. It is everywhere, at full strength, at every point in the observable universe, and it has been that way since about a picosecond after the Big Bang. What we think of as empty space is not actually empty. It never was. And because of that field, particles have mass, not all of them. Photons don't interact with it. Light shoots straight through without coupling, which is why light has no mass and moves at the speed it does. But electrons interact with it. Quarks interact with it. The W and Z bosons that carry the weak force interact with it strongly. Each particle that couples to the Higgs field gets a resonant frequency from that coupling. That resonant frequency is what we call mass, not a substance. Not a substance added onto a particle from outside, a vibrational property that emerges from the interaction between a particle's own field and the Higgs field that saturates all of space. The mass of an electron, the mass of a quark, these are not arbitrary numbers assigned by chance. They are the result of how strongly those particles couple to a field that has been sitting at a non-zero value since the universe was younger than a nanosecond. You exist because of a phase transition that happened before the universe was 1/1,000,000th of a second old. Before that moment, every particle was massless. Everything traveled at the speed of light. The electromagnetic force and the weak nuclear force were unified into a single electroweak force, indistinguishable from each other. Then the universe expanded. It cooled, and the Higgs field, which had been zero in that early hot state, settled into its non-zero value. The symmetry broke. Particles acquired mass. The weak force became weak. The electromagnetic force separated out. And from that moment forward, the universe was capable of forming atoms. Without that phase transition, no atoms. Without atoms, no chemistry. Without chemistry, no stars, no planets, no biology. Nothing with mass could have formed. The universe would have remained a featureless plasma of massless particles racing around at the speed of light forever. No structure, no complexity, nothing. The Higgs field switching on is not a footnote in the history of the universe. It is one of the most consequential events that has ever occurred, and we know this. That's the part that deserves to sit with you for a moment. We know this happened, not because someone guessed it, not because it seems philosophically satisfying, because physicists built a machine beneath the Swiss-French border, accelerated protons to within a fraction of a percent of the speed of light, smashed them together 600 million times per second, and found a bump in a graph, a small excess, an accumulation of data points that shouldn't have been there unless a particle of a specific mass was being produced and immediately decaying. That bump, appearing in the data of two completely independent detector teams simultaneously, each reaching the 5 sigma threshold, each confirming what the other had found, represents one of the most statistically rigorous confirmations in the history of experimental science. 5 sigma, a 1 in 3.5 million chance that the signal was a fluctuation. Both teams, independently, the same result. On July 4th, 2012, the universe answered a question that humans had been asking for 48 years. The answer was yes, the field is real. The particle is real. The mechanism is real. The particle itself is strange. Zero spin. No electric charge. No color charge. Unstable beyond almost any meaningful human time scale. Decaying in 10 to the negative 22 seconds. You cannot hold a Higgs boson. You cannot trap one. You cannot observe one directly. By the time any detector could register its presence, it has already transformed into other particles. Physicists never actually saw the Higgs. They saw what it left behind. They reconstructed its existence from the debris. That is not a limitation of the experiment. That is just what the Higgs boson is. A particle so fleeting that its entire existence is inference. And yet the inference is solid, the properties matched, the mass, the spin, the decay channels, the rates at which it decayed into photon pairs, into lepton pairs, the coupling strengths to other particles, all of it fitting the predictions that the theory had made decades earlier with extraordinary precision. This is what it looks like when a theory is correct, not approximate, not mostly right, correct at a level that spans 48 years of theoretical development and ends with a bump in a graph that matches the prediction to within measurement uncertainty. Think about what human beings actually did here. We asked why matter has mass. We couldn't answer it by looking at rocks or planets or stars. The answer was hiding at energy scales that don't exist anywhere in the natural universe at this temperature. We had to build the conditions ourselves. We had to recreate, for a fraction of a second in a 27-kilometer ring, something close to what the universe looked like in its first picosecond of existence. We had to build detectors the size of cathedrals filled with millions of sensors to track the debris of those collisions. We had to write the algorithms to sift through petabytes of data looking for a statistical signal buried beneath a billion other events. We had to do all of that before we could answer a question that a person could ask in 6 words. Why does matter have mass? The answer is a field. An invisible quantum field that fills all of space has been there since the universe was a trillionth of a second old, and gives particles mass by stiffening the fields they live in until their ripples have a resonant frequency. That resonant frequency is mass. It is not heavy or light in any everyday sense. It is just a number, a frequency, a rate of vibration built into the structure of space itself by a field we could not detect until we built the largest and most complex machine in human history. We built the mathematics to describe it. We built the machine to find it. And somewhere deep in a tunnel beneath the French and Swiss countryside, a field that has been quietly giving matter its mass since the universe was a trillionth of a second old, finally showed us that it was there.